Hello everyone. Today I want to talk about a fundamental shift in how we build neural networks. For decades we have relied on perceptron, the MLP, the multi-layer perceptron layers. But today we are looking at new architecture called Kolmogorov-Arnold Networks, called CANs. Think of this not just an upgrade but as a fluid blueprint that rethinks how a machine actually learns a function. So let's first start with what are the limitations for a traditional MLP. In traditional MLP, you have these fixed activation nodes, and for this, the entire network becomes like a black box. And to explain or interpret why a model does what it does, it becomes really, really difficult, and it becomes internally rigid. And these weights are and these activations in total govern the how a model behaves, but that hurts interpretability and explainability. And also for complex patterns you have to change the architecture completely to probably accommodate further complexity. So let's look at the paradigm shift. In Kolmogorov-Arnold network or CANs, instead of having these weights and in edges and these activation functions and these things, we are replacing the entire thing with functions. And there is it is the nodes do not apply any activations. They are basically simple sum operations on nodes, learnable nonlinear activation functions on edges. So it's kind of flipped around. So the edges now hold functions and the nodes simply sum up. So matrices of 1D spline functions, so replacing linear weights. So previously we would have linear weights in the edges, but this time we have 1D spline functions. So what do we mean by that? So think about a grid of functions. So there are simple spline functions, or these that we call B splines, are in local grids. And then as we get more data on the fly, we kind of nudge the functions in a way and move one function up and down and adjust the functions to accommodate these new training data points. So basically the grid is sparse at first, and then it becomes finer and finer, so to accommodate new training data, and adjusts these you can say nudges or these peaks and valleys. So in MLP, this architecture was very rigid, and once you want to accommodate new complexity, you would need to change the entire architecture. So this is rigid external routing, we're calling it. In CAN, however, this is fluid internal routing. By that I mean this architecture is there. This is like a fixed architecture, but within that there are more degrees of freedoms that are adjusted by these functions, these splines combinations in these edges. So a fixed architecture CAN might be different than the same architecture CAN based on how the internal edges are trained and the internal edges functions are nudged, and how the peaks and valleys are. So you can see how a CAN actually improves than a regular MLP, and the depth to width 10 CAN is 100 times more accurate, than 100 times more parameter efficient than a depth 4 width 100 MLP in PDE solving. And you can see how simple CANs are even expressible and explainable in much simpler terms than any other MLP could be. So this is a very much a plus point for a MLP, explainability and interpretability. So this is the idea that as the training goes, in how it is trained is at first the grids are sparser, and the data points manipulate these grid points in the spline. This is the 1D spline, and as we get more and more data points, these are applied least square fitting to map a fine grained spline to the coarse spline, and then the grids become finer. So this is how each edge goes through the same story, and they adjust based on the data points. You can think about the MLP to be like this rigidly connected string, which you pull in one end and everything else kind of changes, and nothing remains like before. So this is called catastrophic forgetting. So that the idea is that when you learn something new, there is a chance that you are changing the entire behavior and potentially forgetting the past experience, the past learning you did. So but in CAN, however, when some new data points are arriving, you kind of just take one more grid point up, and then these grids become finer, and it's a lot smoother than how MLPs behave or how MLPs change. So the interpretability pipeline from neural net to formula. So the idea is that there is this neural network. This is very much sparse, and then we can actually sparsify that by taking these lower edges, the lower weights or the lesser important edges out, and making into a nicer looking and much sparse network. And then we can actually see, okay, so this right here, let's say this right here, it looks like a sine function, and I can actually snap it to the symbolic function and improve. So the explainability or interpretability got 100 times more easier by looking at the edges and trying to figure out what this edge correspond to in a mathematical term, in a symbolic term. And this is how we can even snap these edges into explainable modules, and then we can actually make the entire neural network much explainable than before. So the idea is a scientist or a researcher can actually perform surgeries, quote unquote surgeries, on these Kahn networks. The idea is that basically when you inspect a Kahn, let's say you're inspecting this Kahn right here in some sort of an editor, and you take a look into one edge and you recognize that, hey, I understand that this looks like this function right here, and why not snap it there and then fix that into the symbolic function. So I recognize this curve as a Basel function, pin it. So, or maybe there would be methods that could suggest some symbolic functions for each edge, and it will go through closer functions that actually match these splines later on. So this makes it much more explainable and regularized. And another important factor right here is that there is this unsupervised discovery. So Kahns are so good at finding patterns that they can discover hidden structures in data without being told what to look for in. In supervised mode, they can find specific formulas. In unsupervised mode, they can find hidden relationships in raw data that standard AI completely fails to see. And they're rediscovering mathematics. So Kahns are applied in knot theory, and you can see how it performs against the most complex architecture of an MLP that has like 300,000 parameters, and a simple Kahn with 200 parameters just beat it. So because it's that many degrees of freedoms more and better, and that it can adopt more data, it can accommodate more data with smaller number of parameters, and this is actually really great. And then you can actually also see that it was applied in physics and phase transitions as well. Kahn helped identify a mobility edge in quantum systems. The Kahn produced an accurate but messy model. The scientist noticed a pattern, snapped the AI basically to specific formula cos HP, and together they produced a clean simple formula for the complex quantum state. So this explainability and interpretability actually helps in regularizing the model as well. And this shared language for AI and science, it can be basically applied in any fields, and you can apply Kahns to many scientific genres and make explainable outcomes later on. So okay, so what should we do? Should we use Kahn or should we use MLP? So here's a decision tree for that. Basically, if you need any of these three things, like compositional structure, complicated functions, or continual learning, just go for Kahns. If not, you can choose either one, because it's not like MLPs are going to be better in the other. It's actually either one. And if you need interpretability, here there is like if this is a high dimension, then either is hard. Like in MLP it's already hard, but in Kahn you have to inspect each edge and probably find some explanation for each of them. But it is actually hard. It's not. I'm not gonna lie. It's actually hard. But if the dimension is low, Kahns are much easier to interpret. And if the level is quantitative, go for Kahn. Qualitative, you can either is fine. It doesn't really matter. If you want qualitative interpretation, it's fine. But if you want quantitative, go for Kahns. Efficiency. So if you want smaller models, go for Kahn. Otherwise, either is fine. If you want fast training, remember Kahns are much slower to train because of the edges are not containing weights only. Rather, they are like tunable functions themselves. So if you want fast training, go for MLP. If you don't want fast training, either is fine, but really go for Kahn if you want the other features later on down the line. Yeah, thank you everyone.